Maxima and Minima. Observe the graph. If you notice, at the point -2, 22, this is the highest point on the graph pertaining to an open interval around x equals -2. Observe, if you will, the point 1, -5. This is the lowest point on the graph pertaining to an open interval around x equals 1. What we want to do is formalize our language. These are both extreme points, but specifically, if we look at the definition, f has a relative maximum at x equals r if there is some open interval r minus h and r plus h for which f of r is greater than or equal to f of x for all x in an open interval for which f of x is defined. In other words, the function has a maximum at x equals -2 if there's some open interval for which f of r, well, f of r would be the y-coordinate 22, if f of r is greater than or equal to f of x for all x pertaining to that open interval. F has a relative minimum at x equals r if there is some open interval r minus h to r plus h for which f of r is less than or equal to f of x for all x in the open interval for which f of x is defined. In other words, the function has a relative minimum at r if there's some open interval around, in this case, 1, for which f of r, which I'll write in its y-coordinate as -5, is less than or equal to f of x for all x in this open interval. The function we have is f of x is equal to 2x cubed plus 3x squared minus 12x plus 2. So for this function, what we say is that the relative maxima occurs at x equals -2, and the relative minima occurs at x equals 1. The actual maximum value, that's the y-coordinate 22. The actual minimum value, that's the y-coordinate -5. Here's the graph, same graph we looked at a moment ago. But let's look at the concept of relative maximum and relative minimum numerically. At x equals 1, well, let's find x equals 1. F of 1, function evaluated at 1, is less than or equal to every f of x near x equals r. That is, for every choice of x in this open interval, r minus h and r plus h. Let's take h to be 0.3 and look at some sample values. Notice that f of 1 is -5. And this is indeed less than or equal to all the other range values when we're a distance of 0.3 of a unit from 1. Now let's adjust our eyes and take a look at x equals 2. At x equals 2, f of -2 is greater than or equal to f of x near x equals r. That means for every choice between r minus h and r plus h for x. Again, looking at a table of values for some sample points, notice that 22 is greater than or equal to all the other range values on this table where we have an open interval within 0.3 units of -2. Now you may be also looking at the endpoints. I'll just kind of draw an arrow to the two endpoints. Let's discuss those endpoints for a moment. F of -3, that would be 11, is not less than or equal to every f of x in an open interval around -3. It is just less than or equal to f of x for an interval that is specifically right of -3. Similarly, if I look at f of 2, it is not greater than or equal to every value of f, for every value of f in an open interval around 2. Rather, it is greater than or equal to f of x for an interval that is specifically less than x equals 2. If I want to talk about what would be the highest point on a graph, I use the word absolute maximum to talk about the y-coordinate at that point. F has an absolute maximum at x equals r if f of r is greater than or equal to f of x for every x in the domain of f. If I want to talk about the lowest point on a graph, then I would discuss it in terms of the y value being the absolute minimum for all the range values. And we say f has an absolute minimum at x equals r if f of r is less than or equal to f of x for all x in the domain of f. Let's look at two graphs. In this first graph, notice that we have a relative max at s, a relative min at t, but the absolute max, the highest point on the graph, occurs at x equals r. Absolute maximum and absolute minimum may occur at the endpoints. Relative maximum and relative minimum, they may not. Let's look at a second graph. Notice we have a relative maximum at s and a relative minimum at t, but the absolute minimum occurs at r. This is the lowest point on the entire graph. So to talk about the types of extreme values, we're going to focus on three types of extreme values. The first is called a stationary point. Function has a stationary point at x if x is in the domain and if the derivative is equal to 0 at that value. So to find this stationary point, set the derivative equal to 0 and solve for x. Second type of extreme point that we're going to look at is a singular point. F has a singular point at x if x is in the domain, but the derivative evaluated at x is not defined. To find the singular point, find all values of x where the derivative is not defined, but the function itself is defined at those points. Now, the stationary and singular points are both called critical points of f. There's a third value that we're going to look at that's extreme that pertains to absolute max and min, and this is at the endpoints. F has an endpoint at x if x is simply at the endpoint of the domain. So here we locate closed intervals that indicate the domain of f if they apply. Look at the first graph, if you will. We have a stationary point at x equals 2 because there is an absolute maximum value of 3, absolute minimum value of 3 at x equals 2. Take a look at the second graph. We have a singular point at x equals 2 because there is an absolute minimum of 3 at x equals 2. Notice the difference, though, between these 2 points. For the stationary point, the derivative is the slope of the tangent line, which is 0. While for the singular point, we have a sharp corner. And this corner results from a slope left and right of x equals 2 on this curve being -1 and 1 respectively. So there is no derivative at x equals 2, and yet the point is in the domain. The first derivative test allows us to look at the extrema by examining the first derivative itself. So our function is 2x cubed minus 24x plus 5. The first derivative test for relative extrema goes something like this. Let C be a critical point for the function. Means you could have a stationary or singular point there. If the derivative is greater than 0, to the left of x equals c means the function is increasing. And if the derivative is less than 0, to the right of x equals c means the function is decreasing. Its graph is decreasing. The result is we can then conclude that the function has a relative maximum at x equals c. But if the derivative is less than 0, to the left of x equals c, and the derivative is greater than 0 to the right of x equals c, we can conclude that the function has a relative minimum at x equals c. And if the derivative has the same sign on both sides of x equals c, f has neither a maximum or a minimum at that value of c. So let's return to our function, 2x cubed minus 24x plus 5. What we want to do is find the extreme points. The locations of the extreme points are first found by finding the first derivative. Derivative of 2x cubed is 6x squared. The derivative of plus a negative 24x is plus a negative 24 or minus 24. Derivative of a constant is 0. Then we set this derivative equal to 0 and solve. So we'll solve by factoring out a 6. And we find x is equal to plus and minus 2. So we will set up a table of values. We will take 2, and if we substitute it into the derivative, we get 0. If we take a value of x less than 2, which is 1, and substitute it into the derivative, then we would have 6 times 1 squared minus 4. It's negative 18. And if we take a value of x greater than 2, such as 3, substitute it into the derivative, we have 6 times 3 squared, well this is 9, minus 4. That'd be 6 times 5, which is 30. So our derivative goes from negative, left of x equals 2, to positive, right of x equals 2. Negative, left of x equals 2, function's decreasing. Positive, right of x equals 2. You can see that we should have a relative minimum at x equals 2. Now let's construct a table for x equals negative 2. Select a number that's less than negative 2, which is negative 30, or negative 3, excuse me. And if I place negative 3 into the derivative, again we have the calculation 6 times 5, which is 30. And if I place a negative 1 into the derivative, again we have the calculation 6 times negative 3, which is negative 18. So the behavior, left and right of negative 2, is that the function is increasing because the derivative is positive, and then decreasing because the derivative is negative, left and right respectively, of x equals 0, or x equals negative 2. So what do we conclude? Well, x has a maximum value. This maximum value occurs at x equals negative 2. Visualize what the graph would look like. A relative maximum at x is negative 2. A relative minimum at x equals 2. And we sketch it. Well, on the screen is the first derivative test for reference. Let's choose another function. F of x is equal to x minus 4 to the 2/3. Let's employ the first derivative test. We differentiate, swing the 2/3 out front, go to the 1 less power. We take the derivative and we write it so that it's written with a positive exponent, and we notice that x minus 4 is a factor in the denominator. So when x is equal to 4, we notice that the derivative itself is not defined. For values of x that are smaller than 4 and we choose 3, we have the calculation 2 times, or 2 divided by 3 times 3 minus 4, which is negative 1, to the 1/3 power. And we get back negative 2/3. And if we choose a value of x that is greater than 4, say 5, we have the calculation from the first derivative of 2 divided by 3 times 5 minus 4, which is 1, to the 1/3. We get back a positive 2/3. Our function goes from decreasing to increasing as it travels from left to right past x equals 4. But because the derivative is undefined at x equals 4, we have an expectation that we would see a sharp corner. Let's observe, if we will, the graph. We have a singular point at x equals 4, but we most assuredly have a relative minima as well as an absolute minima. Thank you.